Hey, how you doing? Phil from statisticsmentor.com here, and today we're looking at differentiation of a function of one variable using the chain rule. Also goes by the name function of a function rule, composite function rule. Now, it works on function of a function. So let's say h is the function of the variable x, function of a function. And then the rule is that if we want to find the derivative of this function, h with respect to x, is df by dg times dg by dx. First of all, this function of a function, this, if you're looking at it first time, looks a bit confusing, so we'll present some examples so that you get an idea of what this means. How do we memorize this thing? Well, if you think about what you're doing here is that dg here cancels out that one, and then you get df over df, df over dx, which is the same as dh over dx. First thing, how do we recognize that we can apply the chain rule? Well, so the function's got to be a function of a function. So here are some patterns. We could have something of the form gx, some function of x, raised to the power of something. Let's call it a. Examples. H equals. So here you got x plus 1 all squared. The g function is everything in here, and the f function is the squared. So you've got h is equal to g squared. Another one is log of something which is a function of x. For example, okay, so here the g bit, the g function, is this bit, which is function of x, and then the f is the log bit. Another pattern is using the exponential function, exponential of a function of gx, which may be written like this, but this is tidier when gx is a long expression. For example, h is equal to the exponential of a quadratic, and the g here is the quadratic bit, and the f is the exponential. And finally, we have a structure involving the trigonometric functions of sine, cosine, basic one, sine, cosine, tan. So I'll take here sine of a function g. Example here is h is equal to the sine of 2x plus x, and the g function is here, and the f is the sine. For each of the structures here, we can see that it's a composite because, or function of a function because, with x we do two things to it. First we feed it into the function g, and with that output g we feed it into the function f. Like so. First we feed the input, the one variable, into the function g, then we feed it into f to get the function. So in the sine here, case here, feed x into 2x plus x to get an output, and then feed that into function sine, the f function, to get h. For the exponential case, first we calculate this bit, which is the quadratic, the g bit, and then we feed that into the f bit, which is the exponential. Then with the log example, g here again is like a quadratic, then we'll feed the output of that into the f function, which is a log. And then in this case here, first we calculate the g bit, here is x plus 1, then with that output we feed it into the function f, which is squaring that result. Okay, so all those cases can be written can be seen as this, and that's why we can apply the chain rule, because what we have is a function of a function. And before we start looking at examples actually how to apply this chain rule, I just have to remark that this chain rule can be applied to more than two functions. So we've got x here feeding into g, feeding into f, but it can be fed into more equations, in which case then, if you're going to use the word function of function, the function of a function suggests there's only two functions, but if we're using more than two functions, then this term isn't really appropriate. It's better to use then the word chain rule or composite function. Alright, so let's look at some examples. Okay, so we've got here f is equal to x squared plus 1 to the power of quarter. You can see that this is of the form function raised to the power of a number. So we can use the chain rule where g, x, let's just write g to be lazy, g is equal to x squared plus 1. Then we can see that this f is equal to g quarter. Yeah, if you substitute this g into here, it's the same as this one. To get the chain rule, we need this df by dg, and then we need to do dg by dx. Okay, so df by dg, we take this one here, we use the standard rule, so bring the power down, g quarter, subtract 1. Now if we're doing that without a calculator, subtracting 1 is the same as 4 over 4. We're doing it this way to get the same common denominator, from which we can see that this is going to be g minus 3 over 4. Next, dg by dx, here's g in terms of x, apply the standard rule to x plus 0. So that's that, and then we put them together. So using the chain rule, we state what the chain rule is, and then we now substitute what these two expressions are. Okay, so just substituting here, and then just cancelling the 2 with the 4 there, 2 in the bottom, and that's the answer. And we note that this derivative, when we have the derivative, we're not done here, recall. We have to state for the values of x for which it exists, and here exists for all x in the real line, i.e. all numbers including fractional numbers. How do we know that? Well, recall we look in here, and we can see that this function exists for all x on the real line. Alright, so using the chain rule for this second example, x cubed plus x plus 1 all cubed, and this function exists for all x on the real line. So here we have f is equal to g3, where g is that bit in here. Using the chain rule, df by dg, you can see from here is 3g squared. dg by dx, we take this one and we use standard rules of differentiation, and then we put it into the formula. So df by dx is product of these two things, multiply them through. We can expand brackets to tidy things up here, or you could possibly leave it in this form, and this is the answer. So we state what the derivative is, and we also say that this derivative will exist for all x on the real line. Okay. Now, is this the only way of doing it? No, because you can see that knowing how to expand brackets, we could also have expanded the brackets first and applied the standard rules, which I'm not going to do here, because you can imagine multiplying this by itself and then the result of that multiplying again with this thing to get a really long expression, and then you can apply the standard results. This way is faster, and that's the whole point about using these rules. Alright, finally let's look at this example here.